We're constantly seeing these incredible things AI can do. It writes code, it makes amazing art, it can answer pretty much any question we throw at it. But there's this giant mystery hiding right at the center of it all. So let's dive in and see if we can crack it open.
For the most part, the answer is a big, fat no. Seriously, the way most of these advanced AIs make decisions is a complete black box. We feed it a prompt, we get an answer, but we can't really trace the logic. But what if we could? Well, some brand new research is trying to do exactly that, to finally pry that box open.
So to kick things off, why is it so incredibly hard to figure out what's happening inside an AI's head? What is it about a standard model that makes it so impossible to read?
Okay, I want you to imagine a brain. But instead of these nice, neat, organized pathways, it's just a total chaotic mess, where every single neuron is connected to every other neuron. That's pretty much what a standard AI model looks like. Trying to follow just one line of reasoning is, well, it's basically impossible, because you've got millions of signals crisscrossing all at once.
And the core reason for this mess actually has a name. It's called superposition. Think of a single neuron, like a drawer in your dresser. In a tidy system, one drawer holds one thing. Maybe socks. But in a typical AI, that one drawer is stuffed with socks and shirts and keys and your old mail. The AI is literally using every single neuron to represent multiple, completely unrelated ideas all at the same time. It's super efficient for the AI, but for us humans trying to understand it, it is a conceptual nightmare.
So, if trying to clean up that messy, superposition brain is just too difficult, what's the alternative? Well, researchers came up with a pretty radical idea. And this right here, this is the key insight. The whole new approach isn't about trying to reverse engineer the mess. It's about training an AI from the ground up with a kind of built-in preference for being simple. You're essentially forcing it to be understandable by its very design.
And this just perfectly illustrates the difference. Over on the left, you've got your standard, dense model. That's the chaotic web we were talking about. But on the right, you've got this new sparse model. Instead of connecting everything to everything, it has very, very few connections. It's forced to create these clear, dedicated pathways. It literally transforms that messy brain into a tidy, minimalist one.
So how in the world do they actually do it? Well, it's a two-step process. First, they train what's called a sparse model, and they force most of the connections to have a weight of 0. And we're talking models where maybe only 1 in 1,000 connections is actually active. Then, to understand a specific behavior, they prune it even more, finding the absolute smallest set of connections, the circuit, that can perform that one specific task.
Okay, so we have our tidy, sparse model. What can we actually find inside of it? Let's look at a real-world example the researchers tested to see what all this newfound clarity actually reveals.
It's a pretty simple task, right? If you start a sentence with a single quote, you have to end it with one. But how does an AI learn that rule? In a dense, messy model, we'd have absolutely no idea. But in a sparse model, you can actually trace the entire algorithm from start to finish. And here it is. The researchers uncovered this beautifully simple two-step logic. First, one neuron acts as a quote detector. It just fires up anytime it sees any kind of quotation mark. Then a second neuron acts as a quote type classifier, and its job is to figure out, okay, is this a single quote or a double quote? Then this other component, called an attention head, which is kind of like the AI's spotlight, uses that signal to find the correct quote type and just copies it to the end of the string. That's it. It's a clean, understandable algorithm.
Now, what's really wild is the result they found. The circuits they discovered in these sparse models are on average 16 times smaller and simpler than the circuits you'd find for the exact same task in a standard dense model. That is a massive leap in clarity.
Okay, so this all sounds absolutely amazing. But as you might have guessed, there's a trade-off. You just don't get this kind of clarity for free. So here's the crucial point. There's this tension between how capable a model is and how easy it is to interpret. As you make the model sparser and sparser to make it easier to understand, its overall performance on general tasks tends to dip. You're essentially trading a little bit of raw power for a whole lot of clarity. But, and this is a really exciting part, that trade-off isn't set in stone. The researchers discovered that if you just scale up the sparse models, make them bigger while keeping that same percentage of active connections, you can actually improve both. You push the whole frontier forward and you get models that are both more capable and more understandable.
So let's zoom out for a second. Why does dissecting these tiny little circuits even matter? Well, it matters because it's a huge step towards building AI that we can actually understand, and ultimately, that we can trust.
The biggest obstacle standing in the way right now is just raw computer power. These sparse models are incredibly inefficient to train. We're talking 100 to 1,000 times more computationally expensive than a dense model of the same size. So right now, it's just not feasible to train a massive frontier model like GPT-4 this way.
But the paper lays out two really promising paths forward. First, we can create what they call model organisms. Think of them as medium-sized, fully understandable AIs. The hope is that they learn these universal circuit motifs that also exist inside the bigger, messier models. Second, we can build bridges. This means training a sparse model and a dense one together and using special maps to translate between them, basically using the simple, sparse model as a guide to understanding the complex one.
And this quote from the researchers really captures the whole vision perfectly. The idea is that by deeply understanding these smaller, tidier models, we can develop a kind of field guide to the algorithms that all these transformer AIs use. This would let us spot them even inside the chaos of a giant frontier model.
Which, of course, brings us to the final question. This research is a huge step towards what's called mechanistic interpretability, truly understanding the algorithms an AI learns on its own. If we can perfect this, if we can reliably read an AI's mind, does that finally open the door to building AI systems that are provably safe and genuinely trustworthy? It's a profound question, and for the very first time, it feels like we're actually starting to build the tools to find an answer.